Hello everyone, my name is Han Guangliao. We are the SAVER team from King Abdulla University of Science and Technology in Saudi Arabia. We call us savers because we are presenting something which can be lifesavers. How? There are athletes who love extreme sports and elder people living alone in their homes. What happens if they fall down or get injured when there's no one nearby? Here, we propose a SAVER wristband to monitor users' vital signs. Once the user is sick, it will report the emergency to medical centers or family member. This wristband is one of the IoT variables. It should be compact and have wireless communication ability. However, the antenna typically radiates effectively when size is greater than quarter wavelengths. So, for IoT variables, antenna miniaturization is really required. Now, this becomes a question for the students who wants to be an antenna engineer in the future. How to make the antenna smaller. Also, this becomes a question for antenna lecturers, how to teach antenna miniaturization. Here we provide a solution. We are presenting a SAVER system in this handbox, which contains not only a life-saving wearable device, but also a great educational tool for antenna miniaturization. By the way, please let me introduce my team name again, SAVER. It does not only mean a life-saving device, it also stands for Small Antennas for Vital Emergency Response. I believe most of us played with blocks when we were children. We used to cascade the blocks to build everything. An interesting question is, can we build antennas like this? The answer is yes. We provide the antenna design kit here in the SAVER box. The kit contains various antenna building blocks. The lecturers or students can easily construct their antennas using the design kit. These blocks are very low cost and easily reproducible because they are all made of 3D printing and copper tapes, which are now very common in labs and universities. With the help of antenna building blocks, teachers and students can build the antenna flexibly. But how can we know if the antenna is working or not? My teammate Yiming will give you the answer.
Hello, my name is Yiming. How do we measure the performance of the antennas? The VNA is usually the first choice, but most of them are expensive and bulky. Therefore, we provide a low-cost and compact VNA as a test bench in our SAVER box. It consists of a pocket VNA, a Raspberry Pi, and a camera. The pocket VNA measures the S parameters of the antennas, and the Raspberry Pi processes the data. For ease of use, we also developed a software called the SAVER Test Bench. The users can set the frequency range, points of sweep, or do the calibration. Now the VNA kit is ready for antenna miniaturization.
We know that for electrically small antennas, the resonant frequency can be approximately expressed by this equation. If we want to lower the resonant frequency, we can increase the antenna's AL or C. Now we are going to demonstrate the antenna miniaturization using our antenna design kit. We start with a simple monopole antenna, which is built by 5 straight sections. Now let's do it 1, 2, 3, 4, and 5. I just need to click measure. Okay, the S11 is measured, and this antenna resonates at 2.4 GHz and it has a bandwidth around 300 MHz. However, this antenna has a height of 28 mm and not suitable for the wristband application. So let's start miniaturize this antenna. It was mentioned that increasing series inductance could lower the resonant frequency. Let's check it by building another antenna using the kit. We remove the upper part first and insert a metered line section on this antenna. And now we add the rest part. Now if we measure it, you can see the resonant frequency is still maintained at 2.4 GHz. This proves that increasing the series inductance could make the antenna electrically smaller. The next stage, instead of changing the inductance, we increase the shunt capacitance here. Now we remove the top part of the previous antenna and we add a top hat structure to this antenna and we click measure. Let's see if it's still 2.4 GHz. Yes, it is, right? We know that the capacitance of a capacitor can be increased when we fill it with higher permittivity material. So now we insert a material with dielectric constant 3 under this top-hat structure and measure the antenna here. Yes, you see that the resonant frequency is moved to 2.25 GHz, and this antenna is actually electrically smaller. Now, this raises another question for us. To miniaturize the antennas, should we increase the inductance or capacitance independently or together? As antenna engineers, we have to consider bandwidth, especially for small antennas. To better match the 50 ohm transmission line, the effective L and effective C should be increased on the same scale. Thus, in the last stage of miniaturization, we optimize the antenna to keep a balance between L and C. We reduce one more section, that is straight section, and we insert a dielectric which has a dielectric constant of 5.5. And let's measure it. Okay, you see the resonant frequency is still there at 2.4 GHz and the bandwidth is around 150 MHz. The antenna is reduced by roughly 60% in height and it can be used for our widthband. But before we do that, we should know how the widthband is designed.
Hello, I'm Zhengliang Yao. We chose the ESP32 IC as a microcontroller of the wristband, and it also serves as a Bluetooth transceiver. To get the information if the user is phoning or not, we placed an accelerometer to monitor the user's movement. A highly integrated biosensor is applied that can measure the heart rate, the blood oxygen level, and the skin temperature. The final PCB we designed have a very compact size of 3 cm by 3 cm. All the data will be sent to user's mobile for later processing.
Hi, my name is Rika Li. Let me introduce how the Android app works to be a lifesaver. This app is developed by our team through the MIT App Inventor. You just need to scan the QR code to download the app. Our app can display all the sensing data in these live charts for the user's vital signs. Once our wristband detects a hot flow, data will be rapidly sent to the app, and it is time that the app analyzes the data and judges if the user has faced a dangerous situation. It will automatically make an emergency call if the user's vital signs become weaker and weaker. Let's see how the app and wristband will work together.
Now as you can see, I'm wearing the SAVER wristband and it is now connected with my mobile phone app. As you can see from my screen recording that my vital signs are already plotted here. You can see the temperature, the heartbeat, and also the acceleration level. For safety considerations, I jump along the way to represent the potential accident, and you can see the fluctuations of the acceleration level. Now I take off the wristband to clearly show the loss of heart rate, skin temperature, and body oxygen level. As you can see, when the heartbeat or other vital signals drop below a threshold value, an emergency call is made to my friend.
At the end, let me conclude our works. The antenna design kit demonstrates the ability of building antenna using blocks. This makes antenna prototyping much more easily and interesting. With the help of the antenna design kit, antenna miniaturization techniques are well taught to students. The proposed SAVER wristband has successfully demonstrated its ability of emergency response as a life-saving IoT wearable. All the designs we proposed are well packed in a handbox, and they are all low cost and easily reproducible. Thanks for watching this video.